things. We can kind of just look at this. The skeleton equation, why they call it the skeleton equation is because it kind of shows like the bare bones of the equation, right, of what's happening. It just shows you the basic molecules that are reactants here. These guys are called our reactants. And reactants always go to make products. Good. Right? So that skeleton reaction, like I said, that's like the bare bones, quote unquote. Just shows you the simplest kind of setup of what's going on there. So it doesn't take into account any quantities or amounts of things. It just shows you kind of who the characters in the flow are. Right. So we have our reactants here. Someone had identified this kind of reaction. What kind of reaction is this?
Combustion.
This is a combustion reaction, right? So we have all these different chemical reactions. And this one in particular is combustion. And there's about 5 other different kind of real general types of chemical reactions, and we'll talk about that a little bit later. But this is a combustion reaction, right? In a combustion reaction, you always create, in a complete combustion reaction, you always create carbon dioxide and water, no matter what. So if you burn gasoline, and you burn it completely, you produce carbon dioxide and water. Maybe you guys have seen, like, when you're driving in your car, and you see like a little tailpipe of someone in front of you, and there's like water dripping out of it. You know what I'm talking about?
Yeah.
That's because they're burning gasoline, which is a hydrocarbon. And when you burn a hydrocarbon in the presence of oxygen, you always create water and carbon dioxide. Now our cars, they're not burning super efficiently, so they also produce a bunch of other gases. So we would say that like a car engine has an incomplete combustion, and it produces other types of things like carbon monoxide or carbon, things like that. But in general, if you take a pure hydrocarbon, which this guy is, it's made up of hydrogen, carbons, sometimes oxygens in there. We'll always create these products here. So, that's our bare bones reaction. Now, we know in the world that there's this law, and there's this law that says nothing can be created or destroyed. You guys know what that law is about? Yeah, also known as law
of conservation
of matter. But energy is also conserved. So in this reaction, we can also observe this law of conservation of matter. And it also goes to energy too, like energy is not created or destroyed. So I think that's kind of where you were going, but similar idea. So when we say like law of conservation, what do we mean by just conservation? You have to keep it. Good. What do you say, Josh?
So basically, matter can't be destroyed or created. It just changes form.
Yeah, it's just changing form, right? So good. So all of these molecules here, right? All of the molecules, and in particular the atoms that show up in these molecules, you'll notice show up on the other side, right? So you'll never have a reaction where it's like H2O plus, I don't know, and A goes to make NgCl2, right? You're like, what? What's over here isn't over here. So if you ever see something like that, that's like red flag, right? So whatever's over here on the atomic level has to be on your product side. Because in a chemical reaction, those atoms are just getting kind of rearranged. Okay. So, in order to achieve this law of conservation of matter, what's something that chemists do to show that?
Balance.
Exactly. So what do you mean by balance it?
You have to have the same amount of carbons, hydrogens, and oxygens. You add a number.
Ooh, good word, a coefficient. Right. So a coefficient is a good word that you'll see in these chemical reactions. And a coefficient is basically a number in front of a molecule. And this number kind of relates to this, what's called a mole amount. If that makes sense. And this number, just like in math, gets distributed in. So if we had like a 2 here, let's say, right?
There's 4.
That means we would have 2 times 2, 4,
4 hydrogens
and then 2 times 1, right? So I'm not going to spend a whole lot of time on kind of how to use these right now, but if we were to, maybe some of us that have seen this balancing act before, can we balance this thing?
Yes.
Alright, let's do it.
You put 3 in quantity.
Multiply by 3.
2.
You put 3.
Alright, how about this? How about you do it on your sheet of paper? And then it's like 2, 4, 2, 3. No, so you can just leave it blank. You could write in a 1, because like 1 times 2 is 2. Yeah. I typically just leave it blank though. Oxygen, what do we got? 3. 3. And carbon dioxide? 2. 2. And water? 3. Alright, so let's go back and look. So we have 2 carbons, and then 2 times 1 carbon here is 2, right? So there's no subscript here, and so we just assume it's 1. So we have 5 hydrogens plus 1 more 6. So then we got 3 times 2 is 6. Good. Here we have 3 oxygens. Over here, oh, we have, sorry, we have 7. Good. And over here, 2 times 2 is 4. 3 plus 3 times 1 is 3.
7.
3 is 7. Awesome. So we've just taken that skeleton equation and put some meat on it, right? And so when I say put some meat, we added some coefficients. And so the skeleton equation is now a balanced equation, right? And that's kind of what you guys were talking about before. So we have these balanced equations which show us now these relative amounts of each atom in our chemical equation. Cool? Okay. Good. And so, in order to make these balanced, in order to make these kind of balanced equations, right, we need those molecules, and in particular, we need these atoms, right? It's that these atoms here basically build to make these molecules, right? And so if it wasn't for these atoms coming together, we couldn't make these individual molecules. And a little later on, we'll talk about bonding. We saw some bonding on that pretest. We'll talk about some like ionic bonding, covalent bonding. And really, in order to get these atoms to stick together, it's all about their electrons, right? It's kind of their electrons that are making things happen in the chemistry world.
Oh, yes, can you do it?
No. Let me take it. I know you guys had a fire drill yesterday, so that's good. Oh, that's drywall. So in here, I have our 2 products, right? I have our ethanol, and I have our oxygen. Right? The oxygen is just atmospheric oxygen around us, filling our lungs and such. So that's accounted for. To take place, I need a little bit of energy. I need a little activation energy to kind of get these atoms to kind of loosen up and kind of react to make our new products here. And so where that comes in is like that. Right? Safety first. Right? Yeah. So reactants in here should be pretty good. We'll do it a little lower. So it's not going to like explode or anything, right? Because it's not pressurized. So all the product, which is going to be this gas, can release out the top here, right? So take a. Looks like you got all your cameras ready. You're good to go.
No.
Sure. Woo! Oh, look at that.
Holy gosh!
That smells good. Right? That's kind of weird.
We do it again?
Do it again.
Again.
You're trying to do it again?
Otra vez, sí.
Otra vez, vamos.
I took a picture right when it happened.
Alright. Do you guys think it'll work again?
Yes.
What do you think?
Maybe.
We need ethanol.
No,
Okay.
Need more. No, put more.
We need more ethanol.
Yeah,
Put more.
It smells good.
Put more ethanol. I want big.
Oh.
You'll notice that's kind of weird, right? Why? What are some guesses? Why isn't this? There's still fuel in the bottom. Look at all that fuel down there.
It created water. Yeah, it created water.
Created water. What else did it create?
CO2.
Carbon dioxide, right? So this whole space now, for the most part, it's kind of leaking out a little bit. But if you think about it, after that reaction, after we took those reactants and we made these new products, this over here was all gas for the most part, right? And so, what do we know about gas molecules? How do we behave? Crazy. What do you mean by crazy and frantic? Moving fast and they spread out. So before it goes out right away.
It kind of went out before you.
Yeah, it almost goes out right at the. Sometimes, so carbon dioxide is actually a little heavier than just the normal air we breathe. Sometimes you can pour carbon dioxide out. I don't know if I have enough of it. No, I don't think I do.
Oh!
But sometimes you can pour carbon dioxide out. It's kind of neat. You can like have a candle or something, and if you create a lot of carbon dioxide gas, you can pour it out and just like extinguish the candle. And it just like. So I'm saying that in verse.
So that water that's in there, that's like water you can drink.
No, that's still fuel. Yeah, so you can see it kind of. So as this fuel just sits and gets vaporized, so alcohol evaporates really quickly. I'm sure if you guys have ever used like Purell, like the hand sanitizer, like it feels cold, right? And so that's the alcohol evaporating off your hands. Right? It's not like this huge like eruption, right? But when you vaporize that alcohol, you basically take all those same really flammable molecules and you spread them out, right? And they're moving and they're more active. And so it often creates this bigger kind of flame from that. And now it's pretty much all done.
You try putting out more alcohol?
You want a little bit more?
Yes.
Do you want a picture? So this is good. We can tie in some safety here, right? As your things in lab, sometimes if like alcohol gets spilled, it might catch on fire, right? Usually, if you're trying to heat up alcohol, you would never use like a Bunsen burner, right? Bad idea. And so you'll often use like a hot plate, something like that. But if alcohol spills and it's on fire, one of the best ways to put it out is to just smother it, right? And it goes out. Depending on kind of the flammable material we're working with, you might use maybe like a fire extinguisher, or you might just use a fire blanket. I don't think they have any in here. But they have blankets designed to just smother flames, right? Right? So you want to smother that flame. You don't want to like fan it or anything, because you give it more oxygen, it can combust better and react more. Especially our girls in here, is to tie back your hair, right? Last thing you want to do is like be working and like you get this really bad chemistry haircut, right? So it's not going to look good. So girls, tie back your pretty hair if you want to keep it long.
Another good thing, guys, is I've seen this before, is